Today we continue our story about density of states. Last time, 2 weeks ago, it was general total density of states. And now I want to show you even more useful concept, which calls partial density of states. Or another name you may see projected density of states, but I prefer partial density of states as a name. Few words about last time, just to remind you what is DOS, how we work with them. We have this space, reciprocal space with these vectors x, k, y, k, z. We had to divide the space somehow into some bricks. Each this brick is a state. What is state? State is some place in this reciprocal energy space where electron can be. So electron can be here, or in any other place, but it's not like all space. So electron can't be in all spaces. It can have some particular energies, and we have seen these energies on band structure plots. So electron can have in some crystal can have only energies from this band structure plot, and we take this space, we divide it into such bricks. What is the volume of this brick? It's just, we can take it from uncertainty principle. So P divided by L, it means that uncertainty of impulse in the space is like P divided by L. I multiply it by 2 because 2 electrons can be in this space. In this side, and I have this volume 2p divided by L in the power of 3. Then I take just the common formula of kinetic energy. I take p squared. Hk is like impulse in this reciprocal space of some particle, and then I can take k from this formula, square from this thing. And what is the volume of this sphere? What is the volume of this part? It's just volume of sphere. P k in the power of 3. What is the maximum? So what is maximum wave vector? It calls Fermi vector, or maybe it's also we can call it Fermi energy or Fermi impulse. It's the maximum energy which can have electron at 0 Kelvin. So at 0 Kelvin, electrons sitting somewhere here inside this sphere, which we call Fermi sphere. Next time we'll work with Fermi energy, and I'll show you how to build this beautiful 3D Fermi energies, and we will build this thing. But now we are focused on this sides. How can I calculate the number of the states inside the sphere? N3D for 3D case, I take the whole volume, this volume, and just divide it by this by the volume of one side. Multiply by 2 L. Then I make some simple mathematics, and I see that number of the states where electron can be sitting is proportional to in the power of 3 divided by 2. And then I can calculate density of states. It's how many these states inside some energy interval. So I should divide it by energy, by year, and I will see that density of states for simplified 3D case, it's proportional to square of year, and I can make this plot. And here all states are filled. Here states empty. What happens when the temperature goes up? How do you think?
The number of empty states is...
Yeah, but how it will be looked in the spot?
There will be a white space and then some blue space and white space.
It will be like this. So here will be smaller. So here and here. Maybe I can even. It's something from Fermi-Dirac statistics. So because electrons, they are. I hope you got this. Yeah, or I should draw it. It's a thing from Fermi-Dirac statistics. When we increase the temperature, some electrons from here, they will be here, and we'll have this, and this border will be smooth. And the bigger the temperature, the smoother it will be. That's the case for this DOS. It's for 3D. For 3D, for very simplified, for some ideal case. For real case, as you have seen, it's not like this. And then I can compare it with 1D, 2D, and 3D systems. Here we have the same logic. For 3D, this volume of the 3D state, volume of our sphere, I divide this by this, get the number of states. Then I divide number of states by year, because it's interesting for us to see how many states inside some energy interval. I divide by year and I get this formula. The same thing I have for 2D case. Squared, it's volume of some circle in 2D space. Here is p k squared, divided this by this, get this number of sides proportional to year. I divide it by year and I get constant. I get some constant, and it means that for 2D case, you have these steps. We have some step on some energy. Then for some another energy, some different energy, we have another step, and so on, so on. We just will multiply this thing on some integer value, and we'll get such interesting density of states. For 1D case, it's also simple. It's even simple. 2p divided by n is the volume of this side in 1D. 2k is the whole volume. I divide this by this, get that n proportional to squared squared, divide by year, and I get this 1 divided by root square from year, and I'll get such thing. This will be for 1D, like quantum wire. So I see that this has a huge dispersion. This states. And for 0D, it's quantum dot is the thing which got Nobel Prize a few weeks ago. We see just this because it will be delta function. It will be delta function for 0D, for 0 dimension of quantum dot, and we'll get the thing. That's why they are so interesting, this quantum dots, because we have very discreted DOS picture, and that's why we can adjust it for some color, for example, which for some color which will be correspond to some energy. That's why they are so interesting, these quantum dots. But we don't work with quantum dots. We work just with graphite, and it's also the thing from last lecture, how we can connect this band structure with dots, because they are very tightly connected. What is here? DOS here, it's just some number. It can be 5 or 6 or 5 on 10 in the power of -2, something like this. It's just number of states inside some interval there. It's some state between, I take some energy, like 5 electron volts, and then I take another energy like 5 and 1 electron volts, and I calculate how many states are here. What is about energy? About with energy, we band structure connected to energy. Band structure is some allowed energy for energies for electron to have in a reciprocal space. Here is for very simple case. We have such parabola-like density of states, parabola-like band structure. and density of state of this form corresponds to this energy. So when we have some flat band, it means that and all our other states, they are on this line. All states about what I'm talking about, they are on this line. And when line is flat like this, so here I see some that it's almost flat, yeah, almost horizontal. I have a lot of those. I have a lot of states here because they are all projected here, and that's why I see a lot of those. Then in the place where our line has the biggest angle, it's the center. So in the center, it has the biggest angle. We have the least amount of those. So when band is flat, a lot of those. When it's it has a huge angle, some huge angle, not a lot of those. And for parabola, we'll have also some DOS parabola. It's for parabola band structure. And some case which is slightly more complicated than just one parabola. But here I also see some mixture of parabolas. It's from Hoffman book, Platina H4. I can also connect DOS for this band structure. So for one parabola like band, it's very easy. We will have such teeth like this. But when we have a lot of bands, they all will be mixed, and we will have rather complicated DOS picture. But we can prepare it. We can take it band by band, and we'll see that it's also understandable. So this band is rather flat, but it's also parabola-like. So here in the center, we will have the lowest amount of DOS. It corresponds to this point. Here we see more DOSes and more DOSes in the corners, and we see such DOS. Then another parabola. Then it's another parabola which is higher in energy, maybe more flatter. We have more DOSes here in this parabola. This region consists of three bands. So one band is here, XY. It's almost flat, and it gives us a lot of DOS. So to this flat band, we have a lot of DOS. Then this parabola corresponds to this things, to this DOS. Here I have a lot of DOSes. Here, because it's also flat region, I have also a lot of DOSes, and in the center, something like here, I have a smaller amount of DOSes, but in the center, I see I have this flat band. That's why in the center I have this peak. And the biggest zone is the biggest band, that's squared. Here is the biggest band. It will give a small peak here. It will give small peak on the other edge, and I see this parabola for the DOS. So even for such even such complicated DOS, we can explain by just a mixture of some bands. I hope that you got it even from last time. And what about partial density of states? All those things which I told, it was about just total density of states. What is partial? Partial is when we take not all energies, not all states from the thing, but we take some particular density of states. For example, I want to see how S orbitals influence on the DOS picture. That's why I take all energies which corresponds to S orbitals. Or I want to see I have some system, titanium S2, and I want to see the contribution from titanium. That's why I take only states which corresponds to titanium. So why it's partial? It's like partial pressure, Dalton's law. So I take this whole picture, this whole DOS, and then I divide it by orbitals, S, P, D, F orbitals. I divide it by atoms, like one kind of atom, another kind of atom, and so on. And what's the difference? Here is some partial density state. So for example, it's some DOS for S orbital. We have the same thing for p orbitals, for d orbitals, and so on. And total density of states, about which I told you before, it's some sum over all these partial density of states. So it's like part. I'll show you some example. Here is two-element material, titanium, selenium, dihydrogenide. Here is total DOS. This what we have built last time, and it's here, and this is its band structure. We see that at zero, at Fermi level, we don't have a lot of bands. That's why at Fermi level, I think it should be somewhere like here. We'll see not a lot of DOS. And I want to get from what orbitals consist this band structure. And I have to split my total DOS picture into partial DOS. And here I'll see titanium 3D. It's a titanium orbital, which gives very high contribution on this energy, from 0 to 2, this titanium 3D. I see where is 0, 2. 0, 2, it will be something like here. And I see that these orbitals, these bands, they correspond mostly to titanium 3D. And that all conductivity in this material is because here we have 3D electrons for titanium. Then I see selenium for p orbitals, they have higher contribution here, so under Fermi level. So most of this bands, there are some mixture between selenium 4p and titanium 3d. All these bands. These bands, they are it's titanium 3D bands, and this is selenium plus titanium, and we can say what orbitals play a role in conductivity. What orbitals play a role in this valence zone. So from what orbitals our electrons goes inside. We can say that if this material becomes conductive, it means that highly likely electrons from selenium 4p orbitals, they will go from here somewhere here. So they will go to some 3D titanium 3D orbital. So we can say about some electron exchange of this thing. Next week we will build Fermi surface of this material, titanium selenium 2. And what we will do today? Today we will calculate this pDOS for graphite. A few last times we have worked with graphite from about months ago. We have built band structure of graphite, then we have built band structure of graphene, and we see we make this research for more and more complicated. I add some new things to this research. We have calculated band structure, and the last time we also made this band structure. Then we have calculated DOS, total DOS, and today I want to show you how we can build this pDOS things. And we can start our okay. It's not so it's almost the same as for total DOS, but with some additional things like this, some pDOS things, but I will tell you about them when we'll get to it. I'll say a few words about the algorithm just to repeat how we can do it. First step, relaxation. Why we had to do it? Because the materials we take, they are not in ideal positions. All these atoms, they are not in ideal positions. They have some stress, and that's why we should release the stress, release the velocities, and relax it into some state. Relax it into some some ground state. Then we take this structure from relaxation to self-consistent calculation. We have done it already. Self-consistent calculation, we calculate energy and calculate Fermi energy. This self-consistent calculations. Then we copy all this data from self-consistent calculations. We get some psi functions for some electron density for our structure, and we calculate band structure along some path in brilliant zone. We have done it. Then we can, for another path, we can calculate DOS. For DOS, we had to do some additional things, which calls non-self-consistent calculation. It was know-how from last lecture. And what is the difference between self-consistent and non-self-consistent? In self-consistent calculations, we just work with quantum cycle. We take some electron density, we put it in some cycle, then we see how it will be calculated till convergence. For non-self-consistent calculation, we take pre-calculated wave function. So we have electronic density calculated from here. All these files, all this 90 megabytes from the folder, it's like calculated electron density. I take it into the folder where I want to calculate a non-self-consistent calculation. It will take this electronic density as input and then make this cycle once more, one more time, this quantum cycle, but with pre-calculated electronic density. And we can increase at the step. We can. What's the main difference? Occupations. Here it was like smearing, Gaussian, the Gauss, all this stuff. It means that we smeared electrons, these electron states, somehow in these bands. And then I used tetrahedra opt. This tetrahedra opt option, it's tetrahedra way of integrating the brilliant zone. And it allows us to get really precise data, because all these doses we need really good integrated brilliant zone to calculate doses. Because for example, I in my presentation we have this peak. Yeah, we have this peak, and if I will take not enough k-points when I integrate my brilliant zone, I will not give this peak, or this peak will be smooth. So we need a lot of k-points to get good DOS picture. That's why we use this non-self-consistent calculations with tetrahedra opt, which is good for DOS. It almost we will use it only for DOS. And I increased k-points number. I increased it at least twice, but maybe twice is also not enough. But it's something. It's something. Have you copied it into your machine? We have this folder, and what we can see here. This is the folder from lab 6 with where those part was calculated. Here I see this SCF where is this? SF in, SF out is from SF calculations. We have done it last time. Then I see this NSF, non-subconsistent calculations, two NSF files in and out. And then I see a lot of such files, graphite DOS in. It's just files from total DOS which we had calculated. And now, so we don't need these files today, but I just copied all. And I have this thing. This is the most important, graphite save. It's a folder with wave functions. This folder gives that 90 megabytes in weight. It's all wave functions for this structure. And each file is like, it's binary files. It's like, yeah, 0.3 megabytes, but we have a lot of such files. And we have new file. It calls pDOS in. I can show you the difference. Last time we had this DOS in file, and here we have pDOS. I just called it pDOS. And we use different models to process with them. For DOS, we used DOS.x. It was this file. It just prefix name of our folders, our dir where pseudopotentials are. Fill DOS, it's the name of file I want to create. And delta E, it's our energy step. What is delta E? Delta E is the thing from here. It's just DE. It's some delta E. It's the interval where we calculate our doses. And partial density of state, it's almost the same, except we use not DOS, but projwfc. WFC, it means wave functions. Proj, it means projected. So it's like we take our DOS and project them on wave functions, on s orbitals, on p orbitals, on wave functions of some atoms, and so on. And the difference, it's not fill DOS, but fill pDOS. And that's all. That's all difference. I use projwfc.x module to deal with them. And I just started like graphite pDOS in, graphite pDOS out, as we have done a lot of times. And we should wait a while. Okay, we get the output. In our output, we have this huge file. Where is it? Graphite pDOS that. But it's divided. You see, graphite pDOS that, pDOS ATM 1C WFC 1C. So what happens here? It just some graphite pDOS that, it means the name we had chosen in our file, and then it means partial DOS for atom number 1. We have graphite, so we have just C atoms. Atom number 1 for wave function 1. What is wave function 1? It's S orbitals. Then I have another file for wave function 2, it's p orbitals. And then I have the same files for another atoms, atom 2, atom 3. If our system had d orbitals, we had 3 files for each, one s, one p, one d for each item. And each file consists of some data. So here is energy with step 0.01. I have chosen the step. Then LDOS, it's like total DOS for this thing, and pDOS is partial. It's our S-DOS. I have it in my presentation, the slide here. So energy, L-DOS, it's some total doses, so we just sum them. And then we have pDOS 1. For S orbitals, we have just one column for S orbital, because S is like, it's S. For P orbitals, we have more data, more information. You see. Total DOS, total pDOS for P orbitals. And here is PZ orbital, here is PX orbital, and PY orbital. We can divide these orbitals. Maybe Igor is right, and here here it calculates DOS in two base. It calculates is as a whole DOS, and this is it, and then it calculates each subsystem, for each atom, and then just sum up them. And they are almost the same, but you see that we have some small inconsistency, like insert digit. It's not huge, it's not big deal, but yeah, we see. I think that if we get more points, we'll get this inconsistent lower. Okay, and how we can plot all this stuff? I should, for example, I want to plot S orbitals and P orbitals and total DOS in this in my plot. What should I do? I should gather all information from these files. So I should take this energy. I should take this pDOS for S orbital. Then I should gather it for each atom. For atom 2, the same thing. So then I should take it from atom 3, and so on. And we have a very useful option in Quantum Espresso for this thing. Some pDOS is another model. And I can show you how to deal with it. Just model some pDOS. What means these stars and these things? It means that we should take only files where is big C letter. It means that we don't star means that we don't care what is written in this file before S C, and we don't care after C. And we look only for these files. So it's like and slash and the thing, it's like just how we can write it. So we can't write it just star C star. We should do it like this. It means that we take all these files. So I take one file, another file, third file with C, and then I took all this data and collect into this file. It means that the arrow means that we collect this data to this file, C total DOS, and I just type its name, total DOS. No. It means that it takes these files as input, and then it will work even without that arrow. You see, reading file graphite pDOS dot atom C. It means first star. It means that we take all these things, all this long name. It's first star, and then all this long name. Oh, it's this part of this name. It's second star, yeah, and we have only C. So it took only atoms which has C. It didn't affect on some other atoms. But now we have the C total DOS, and it will affect it if we will do it again. It also will affect it. Okay, and I do it in the same way. In the same way, some pDOS, then arrow C arrow, like star C star as for previous thing. And now I want to choose not only C but also S. This S, and that's why I add star and S. S in the S stays in the end. That's why, and CS date. Yeah, you see, it took only files where there are S, C, and where are S, small s, only for these files. And the same thing I should do for P. P and P. Don't forget to change the name of date and P here. And now we have just 3 files, and we work with these files. It's just it's just very simple dot files. Total DOS dot. Yeah, I think Igor, that you were right. I want to compare this. Where is total total DOS? I can compare it. You see, by using this by applying this sum pDOS, I just took each DOSes from file and just sum up them, and I got this thing. And it's the same as here as pDOS. You see, so pDOS is the sum. No, it's not like this file. It's like total DOS. Right second. Yeah, here. Yeah, you see, it's the same as second row. Yeah, so second row is a sum, and DOS here, it means that they took some other option and calculated the whole DOS, not the sum. Case solved. It's total DOS. The same two columns I'll have for S DOS, and here I see S sum S for. I see that we have some chat. SD and Poppy. And we just had to plot these 3 files. And I created this script graphite pDOS py, and let's just Python 3.7 pDOS py. Let's see. And I will explain slightly later how this how it works. Hope you get the same thing, the same picture. You mean between this blue and this? Yeah, this is P states, and you see that for this they almost the same, but in some places like here or here it's not the same, because this sum of our DOSes, total DOS, it consists of sum of pDOS, P states, and S states. And here we have S states, here this S states, and we have P states, this P states, and they get this total DOS. But here we have very low amount of S states. That's why they almost consist, but almost, because we have some small amount. But here they consist almost exactly, because we have here very low amount of S states. Yeah, last time I showed you such thing like integrated DOS, yeah. And it was if I will take all these DOSes and sum up them, all these DOSes, it will be number of states. Number of states, it's like 2 times lower than number of electrons. It will be 16. If I'll take all this DOS, all this thousands of DOSes we have this data, sum up them, and I'll give 16. Theory of graphite, we operate almost always with p electrons, because we have this flat thing, and this p states like pz, px, py, they make these connections in graphite. Yeah, and so when we have some conductivity in graphite, it means that some electrons from p state, from here, they go somewhere here, and we have this conductivity. And also we have this mysterious S, yeah, here is mysterious S. And I have some presentation part for it about hybridization. So we see this hybridization. Maybe you heard about this thing, maybe you worked with it. What orbitals we have? 1s, 2s, 2p. We have 4 electrons. Yeah, but you see, maybe I was mistaken. It's not like 1s because we have 4 electrons. We have 4 valence electrons for graphite. 1s very, very deeply. It's very, very deeply. So it's like part of 2s. But why we have it splitted? It's really mysterious. Yeah, but common sense tells us that all s orbitals should be here. And all 1s orbitals, they are very, very deeply in the energy. We don't see them because we don't include them. We include only 4 valence electrons. What's the story? How it for conductivity we have these 2 electrons, 2p, px, py, and then this electron goes here on p state, on pz. This electron goes here, and we have 1, 2, 3. We have 4 orbitals. 4 orbitals, each of which can take another electron. The real system is slightly complicated. I like this picture. For S, how to memorize that for S before 3D. The picture is slightly complicated. Yeah, that we have also 3S, 3P, 4S, and so on, but they are empty. The states are empty. We work only with these things. On next laboratory works, we will work with transition metals which have 3D. Yes, and we'll see how it's how many complicated things it gets, because we have this four orbitals like x, y, z, z squared, and so on. But here is just graphite, and these 4 orbitals, they can be we can deal with them as with 1 orbital, with 1 hybrid orbital, and it calls hybridization. For example, sp2 orbital, it's planar graphite. It's graphene or this layer in graphite. S orbital, it's like sphere, and 2 Hantel p orbitals. They are mixed, and we have 3 sp2 orbitals. Why we do it? Because it's easier mathematically to work with such orbitals, and of course, it's some physics stays behind. We have 3 orbitals with this. Okay, it's full circle, and we see this like Mercedes-Benz symbol, and it's planar. It's planar graphite or graphene layer. And in this plane, we have very, very strong orbitals, very strong mixtures. And 1 orbital here stays here, pz orbital. And this pz orbital, it's like, or maybe I can draw it. I have this plane, this plane, this plane. It's graphite. Yeah, each of these planes. If I will see. If I will see on the top, I see this honey things, yeah. And here is some atom, and here our orbitals are. This sp2 orbitals are here. But we have just one left, pz. It means that pz should be like here. Here is pz. And here also we have pz. Yeah, here we also have pz, and here we have pz. And that's the case behind this layered structure of graphite. That they are connected, these layers, they are connected by these pz orbitals. This is p orbital, is p bands. You're laughing because this picture so wet. Okay, and we have this, and there here in this plane we have sp2 hybrid orbitals, mixtureless orbitals, and here is pz. And what I can, what we see here, we see this hybrid orbital. We see because each hybrid orbital, it consists of some part of s and consists of some part of p. Yeah, part of p here. So we so here there should be some pz orbital, and here will be here and here will be sp2 orbitals. And we see this mixture. Here we see the mixture, and here we see the mixture. This is how we can see it in the plot.
So once again, this part in the conduction bond corresponds to
some s part. Yeah, because they are mixed.
Yeah, of course. But for the lower one, is it like the unmixed part of s orbitals, or it's also?
It's you see, when it's mixed, we can say that we have this 3 parts, and only 1/3 of it is s. They are mixed. They're totally mixed. Yeah. I don't remember where this s part. This s part can be here in this flower. So they are interchanged very in very strong way. This orbitals.
But on the density, the partial density of states, this
it's some part of s, and here also some part of s. Here some part of s, and here some part of s.
Both of them are
in
hybridized.
Yes, it's some part of sp2 orbital.
So it's not like s orbitals only partially hybridized. Or
no, it's fully hybridized. Yeah, it's fully hybridized, but it's splitted in such ways. And here we'll see only pz. Here will be only pz orbitals. Okay, so a few words about script. I hope it's not very complicated. What we need to specify here? I specify name of files. So DOS, total DOS, CS, CP, Fermi energy, which I get from SF calculations. Then I just specify some limits y, x plus 0, 3, minus 10 to 10. And here are two functions to read this data. So one function, I read data from a file, because we have the same files, so I can do it with a function. So like as input, I have here name of file. Then I say that DOS data is all information which I contain in this file. Energy levels, it's the first row, DOS data 0. DOS values is the second row, and that's all. And I return energy levels and DOS value from this function. And the second function, plot DOS function. Each gets energy levels, DOS values from here, and gets some legend. It means that how I will name it, like total DOS or S states or P states or something like this. So I just plot like energy levels minus Fermi energy, because I want to scale it on Fermi energy. I want Fermi energy to be 0. Those values, just 2 parameters, and legend. Legend is like name, total DOS. And that's all. Fill between X, it means that I fill with some color O space between X and this line. Then I create some vertical line, like some horizontal line. I give them parameters. I apply limits on the plot, on Y and on X, and I plot legend. That's all. Nothing special. And then I just plotted size of the DOS, then plot DOS. I call this data, energy levels, DOS values in this plot DOS by this function. I input here DOS file, name of DOS file, and I write total DOS. It's just legend. It's the same for S states, the same for P states, and then I plot it. So it's this plot is very simple. Now we can plot both band structure and DOS. It will be graphite, band, pDOS. You also have the script. Ta-da! It's the same script as we used last time, but with some upgrade, with some little upgrade. So I just connected two scripts, one script for bands, one script here. For those made supports, and this is one support, this is another support. And I see we see the same picture as we saw last time, but also upgraded with some colors, but in color. The same, but with color. With less artifacts. No, I see. Yeah, I see that we have here a lot of artifacts because of the thing. So because you see, it should be touched ideally, but they don't touch ideally. See, it should be very smooth, all these things, but yeah, and you see that these bands correspond to a mixture of P and S, this hybrid orbitals. These hybrid orbitals and these bands, they are also stands for hybrid orbitals, because we have here S and we have here P. So these bands, they are hybrid, and these bands are hybrid. And these bands, they are P bands. And what is P band? It's PZ. And we can also build PS, PZ, PY, and PX, but I forgot to make a script for it. We can do it last time. I begin to do it today in the morning, but then I thought that okay, I'll do it next time. So we can also divide this plot into PX, PZ, and PY. And in this case, we'll see that these PZ orbitals are here. Okay, maybe you have some questions about, because for model you had to make it for some other structures. And describe it. Describe what we have here. We can also let's make some thing. For example, I want to build not S and P states. I want to build the contribution of first atom, of first C atom. How can I do it? I should play with this some pDOS. Yeah, I think you're right. The task is how we can see the contribution of first atom. We have 4 atoms. I want to contribution of first 8. So from some pDOS, I want to what is the think of it? It's like ATM 1. Yeah, I can choose ATM 1. ITM like 1. Yeah. It will be like C1 S1 DOS. S1 DOS. Let's try. Yeah, you see it worked. It chose only these 2 files, ATM1 and ATM2. Now it's not very interesting to see the contribution of C atom because it will be the same as total DOS, but 4 times lower. But it will be useful when we will work with more complex structures, and we can see the contribution from titanium atom, from selenium atom, from other things. What file I have? I have C1 DOS, and I had to change my script in some way. It's like DOS1. What should I change here? I want only 2 atoms, so 2 plots, total DOS and this C1. So I have this C1 DOS file, and I don't need it. And I had to change here something. Total DOS and C1. I guess I made copy. I copied graphite because I don't want to change original script. Yeah, you got it. You got the changes. Just name of the file, and here I just removed the third line, and I just changed the legend C1, and that's all. It's very, very simple. And what's the story? That's improvisation. I don't know what we'll get. Graphite pDOS 1. But I think we'll get something. Yeah, what I have predicted. The C1 is the same as this as the total DOS, but 4 times lesser, because we need 3 more atoms to fill all this DOS. We still have this artifact, you see, yeah. Y-axis here, how do you think what is it? It's number of DOS. It's number of DOS, number of states. So it means that, for example, from 0 to 0.1, we have like almost 0. But here we have a lot of states, yeah. But 1.5, yeah, by 1.5 for very small energy interval. That's why we need very flat band here. Yeah, it's a number of states per energy interval. Yeah, you also got this spot. And I think that from my side, it's all for today. Maybe you have questions. Yeah, you don't have questions.
I have a question. What will you need to describe in our follow-up?
I will think about it. Maybe today, maybe tomorrow. You mean you last time on last module you made the perfect description of what it just you can try to describe it like in scientific papers. So we see here we see band structure, we see DOS. We divided DOS into S and P states. This S conductivity of this material almost fully depend on P states and so on. So all information you can say about these pictures, you should write, and it will be useful. Now for the
Total number of items to use, because on the file it follows that we have 4 items.
Yes. Yeah, for S and P, yeah.
It is dependent on the 1616 below the file, or
You mean 1616?
yes,
This. Oh no, it's it.
Points, but,
Key points. No, it don't depend. Key points. The number of items depend on this 1, 2, 3, 4. We have 4 atoms. Is a unit cell. We have 4 atoms. For each atom, we have 2 orbitals, S and P. Yeah, and that's why we have 2. If we have, for example, here 1 titanium atom, it will be 1 atom, and we have 3 files because it will be S, P, and D.
So if we had a cubic structure, we would only have 1 atom per unit cell.
2 atoms per unit cell in cubic. Two atoms, yeah, and for each S and P, yeah. It depends only on number of atoms and of nature of this atom. So for today it's over. Thank you very much for your attention.